lab as possible.
Right. So now we will just go in with the audio like that.
Yeah, there's like one of the labs.
Looks like it's even recording.
Okay, check.
Okay. And so probably what you should do then is you'll need to like find whatever the Zoom, I don't know if this is on my account on Zoom or what, but I launched it. But we'll need to find like the addresses so we can send it out, right? Zoom screen just reflects camera, right? So if you want to go center stage.
With like just doing things like
So
I
want probably just
yeah, you probably should just like grab. I don't know if we, there's a chair over here. Yeah, there's a chair. So you can just kind of sit over here, do what you need to do, and maybe we'll find out a way that you can do a laptop or something. I don't know. So let's see. Got a couple. I can hear it. Okay, we can try that once. Right, maybe we'll just move outside and try it one day. Okay, but we're going to try that after. This is my first time teaching in transport, so I'm doing new prep stuff. So I can't do too much fancy with making videos and stuff. So maybe if you were in my fluids class or something else and make videos, and I'd love to do that for here, but there's so much work just prepping that class. You can't do it. So anyway, so we're going to try and do this. Someone's got it. How's it working? Okay. So anyway, we'll have to see how that goes. I'm certain it's worse than being here in person, but probably better than nothing. We'll see how it goes. All right. We're all figuring this out. This is time for class to start. Why don't we have an opening prayer to give us a start? Anybody that's all to give us a prayer? Okay. Yeah. Here goes Zach.
Heavenly Father, we are grateful for this day, and we're grateful for the opportunity that we have to start a new semester at BYU. We ask you to please help us in all of our endeavors, that we may be able to schedule our time effectively, that we may be able to understand the things that our teachers will teach us, especially Dr. Tree at this time. We ask you to please bless him in this preparation of this new course, that he may be able to teach the material in such a way that we may understand, that we may be able to be pushed and have questions and be able to work to understand this as well. We're so grateful for our opportunity to be here as students, and we ask you to please help us that we be able to help this university, that we be able to resist, that we be able to stay open during COVID-19. And we also ask you to always help us to look for those people around us whom we can help and lift up. And these things we pray in the name of Jesus Christ.
Amen. Okay, so I'm going to do the following when I lecture. I'm going to take off my mask, I'm going to throw on the shield, I guess. Okay, because at least I think you can see my facial expressions a little better. Is that okay? Can you see me? I feel stupid because I've got a clear mask on, but also echoes in here, so it's kind of weird, but we'll see how that goes. It's terrible talking in a mask. I don't know if you feel the same way. It's like, it's one thing to sit at a desk for a while and do this for an hour. It's another thing to like talk for a whole hour. Anyway. Let's see. So we have 10 in here. Is that right? 10 of you. Okay. We all found our seats. I think BYU wants us to wipe our seats down when we first come in the room. Like, but I didn't see any wipes. Did you guys see anything like that? Are they back there? They're right there. Okay. So next time, I think when you come in, they want you to just grab a wipe and wipe your seat down. All right. Okay. Let's see what else. Go over this slowness. So we're going to try something. I didn't try before. So put my computer and that screen. And we need to screen which ones. I think it's there. You see the arrows? Thank you. Okay. It's just not centered. Just not nearly steady. Okay, so a couple things. Yes, I got one more thing to put up here. This is going to be obnoxious.
We'll just stand up on the desk and push the projector to the right.
If you would, that would be awesome. Yeah. Perfect. Look at that. Okay, you already have extra credit. You might be an engineer or something. Okay, so we have a course website right here, transport phenomena, class. Okay, you can see all the stuff I have today, the syllabus, the course schedule, the schedule is on the website here. Okay, so syllabus is the first page. Come here, here it is right here, and some of the syllabusy stuff that you want to know at the top. Okay, I'll put the course notes in here. I'm not going to put my full lecture notes, but I'll put supplementary stuff up there. Homeworks. Our homeworks will be mostly from the book, but if there's anything else, I'll put those up. That kind of stuff. Okay. So let's see. What are the things I want to tell you? Back here. Just want to think about a couple items of business before we really get going. So first thing is, this is a graduate course. It's a core graduate course of chemical engineering. So I think we have at least one ME, and I don't recognize you. Remind me your name again?
Zach Wallace.
Zach Wallace. Okay, we got Zach and Zach. Okay, so welcome. I'm excited to have you. Are you a graduate student?
Yeah.
Perfect. Great. And I think we have one undergraduate in here, just Zach, right? Okay. So for the undergraduate, I don't mean to pick on you, okay? But I'm going to just tell you this class is going to be rigorous, okay? And so the graduate students in here, they have 3 classes this semester. You probably have like 5 or 6. I don't know your schedule, but they're going to have 3-ish hours of homework per class period, whereas the normal advised thing for an undergrad class is 2 hours of homework per class period. So it's at least 50% extra work, and it's kind of hard, right? So this isn't for the faint of heart. I'm not trying to like tell you can't take it, but just be advised. I want you to know from the beginning that this is going to be a graduate class and we're going ahead, right? So if you're on board and that's exciting, perfect. I'm glad to have you. Okay. Other graduate students are like, great, I can't go. We have our TA, ChEn. Do you want to stand up and just introduce yourself, ChEn? Tell everybody who you are, how far along in the program you are, who your jerk of an advisor is.
Well, that's you, apparently. So I'm ChEn. I'm starting my 3rd year PhD here. So I work on polymer simulations. So currently I work with Dr. ChEn. And it's an honor for me to be your TA this semester. So have fun.
Okay, so ChEn was a TA for transport last year. She probably got an A++ in the class. I don't really remember, but she's super bright. So I'm sure she'll be a great resource for you. So we're going to talk about transport in a minute, so I'll sort of skip over what we're going to hit there. The textbook for the class is Transport by Bird. Sorry, it's a little late going up. I was trying to debate between Transport Phenomena by Bird and a different book by Bill Dean. We're going to stick with Bird this year. I sort of think of this class as having 2 sort of broader objectives besides just like learning the specific things we're gonna talk about. So the first, I think I mentioned this in the orientation on Friday, is that in an undergrad class, we're trying to teach you enough to be sort of competent engineers, right? But in a graduate class, there's this frontier out here where research happens. And we're trying to take you from where you left off at these undergrad courses and get you at least a foundation so that you can start to contribute out of that frontier, right? So we're trying to build your foundation and try to get you to know enough that we can get out to that edge, okay? And that means that, like, you know, in undergrad, if I like skip a thing or make it a little easier, maybe it doesn't matter that much, okay? But if I don't tell you something important that's real, that really exists out there, right? Then you can't understand the literature, right? You can't do your research. And so that's important. You're gonna spend a lot of time in your degree, whether it's a master's or PhD, doing research. And so we need to sort of take that gloves off and do the hard stuff. Okay. So that's one of the things I view my job in this class, pardon me, in this class, is to help you know what you really gotta do to be able to get there. Okay. The second thing is I actually really love transport phenomena. It's a bunch of the stuff I do for research. And I hope that comes through a little bit in the class. Maybe if you've had a class with me before, you already know I'm a huge nerd. I actually really like this stuff, okay? And transport is a beautiful subject. There's a lot of mathematical analogies between the various disciplines. It's really interesting. There's a lot of fun things you can do analytically to solve problems. There's a lot of deep insight you can get into the way the world works and through transport phenomena. So I hope that you at least come out of this class a little bit with some appreciation for the subject and some excitement. Okay. So as for the sort of mechanics of the class, it's going to be lecture based. We just talked about the Zoom thing. There are reading assignments on the schedule that go with lecture. I assume in my lecture that you have not necessarily read, but you may have read. Okay, I'm going to lecture about what I think are the important topics. And then I view the reading as a supplementary material, which I highly advise that you do, but you do sort of in conjunction with your homework. That's kind of the way that's kind of the way I structure my classes. We're going to have homework assignments. They're going to be due weekly. At the beginning, I think most of them are due on Mondays. So they'll be due every Monday for a while until the first exams, and I think they switched to Fridays. I can't remember. Sort of based on where the exam is and it flips us. So you can look at that. I think there's 13 homework assignments. So they'll cover 3 lectures usually, but some of them don't cover all 3. They might cover 2 lectures. We can look at that on the schedule if you're curious, but I think you guys are mature enough grad students. I don't need to hold your hand as you look through the schedule, but please ask me if you have anything that you want to talk about. We talked about TA. Group work, you're encouraged, of course, to work together. For the homework, we're gonna go all paperless in the class as much as possible. Okay, so to do the homework or to turn it in, just scan it, make it into a single PDF, and turn it in on. Okay, to make it into a single PDF, there's different ways. So if you go to the Clyde building on the 4th floor, there's a scanner there that will send you a PDF, and so you can do that if you have access to the Clyde building. It's not 2 in the morning or whatever, okay? I don't know, I had students turn something in once and they texted me like 11 at night. I can't get in the Clyde building, I'm sorry. But you can also take pictures with your phone, okay? Get a bunch of images, and then I put some links on the course website to some websites that will take a bunch of images and turn it into a PDF for you if that's
There's also the Adobe Scan app.
Yeah, there's that too. So I put a link to that on the website too. So at least, so there's a bunch of different options for that, but we would really prefer that it be in one PDF and not in like 13, JPEGs that you took pictures of. And also, if you're going to take pictures with your phone, which usually works out great, just do a good job, right? Actually like turn it like horizontal and stuff, because the TA is a really hard time like seeing homeworks that are like this, and then trying to read. And in this class, we're going to be doing a lot of mathematical derivations and other things for transport, right? And if you're writing really tiny and then you're taking pictures like this, and Chenu can't read it, she's just going to yell at I'm not going to do okay? She's not gonna start. One of the things I wanted to say is that, okay, we're all like grown-up, mature students here, right? And as I told you in orientation, I want you to call me by my first name, Doug, instead of Dr. Tree, because you guys are grown up enough that you don't need to have me, be paternalistic and tell you all the things you need to do. Stuff. You're graduate students now. It's, you're here, you're ready to go. You're adults. Like we can take off and do this. We don't need to, there's of course questions, and I'm not trying to be, patronizing or like whatever, but I'm just saying, like, I want to treat you like an adult. I want you to, to act like an adult. I expect we can all do that. And we're not freshmen anymore. We can function in classes. You guys are pros at this. You know what you're doing. Late homework. I understand late homework happens sometimes. We'll take it for 50%. Okay, so if you're late, please still do the homework. You'll get learning out of it. We'll take it for 50% credit. We may or may not grade it depending on what happens. We may just take and give you 50%. We'll see how much effort it takes to do that. We'll have a couple of midterms and a final exam. Regrade policy, just talk to me, okay? And I'm going to ask you, if you ask me about something, like, of course, we might make a mistake on grading, we might mess it up, okay? Please just let us know. But I'm going to ask you to email me. So even if you tell me and you have this tiny little thing and it's super easy, I'm still going to ask you to email me because it's the system I use to keep track of these kinds of requests. Basically, if you're asking me anything in class, I'm going to ask you to just send me an email because it's a lot easier for me to remember than if you just tell me in person. So I appreciate that courtesy. Grading, there's a grade scale. I wouldn't worry too much about the grade scale at this point. We'll have to figure that out. My goal in here is not to give you all like D's. Okay, my goal is that you all have an A when you leave. I view my role as an instructor, as a teacher, sort of like a coach. Okay, there's this material. I think it's really fun and interesting material. I'm trying to structure it in a way that we can best learn, but I can't like do the vector of calculus for you, right? Like you have to do that and learn it. And so I view my job hopefully as a motivator and as a person who's helping us stuff to practice. And I hope that we can all get an A. Of course, in graduate school, the point of our, certainly by now we should all realize, right? We're not in this class to get an A. We're in this class to learn the material, right? You didn't come take this class because you care about an A, right? You came because you want to learn the material. And so we're all here for that. And so the grades kind of, hopefully, we'll try and be as fair as possible and make it work out, but hopefully we don't have too many anything below B pluses in this class. Everybody should be doing well. But if you're struggling and it's really going rough for you, come talk to me. We'll try and help you out. See what we can do. But the grade scale will likely shift. Okay, like I'm going to give our tests and other stuff, and then whatever this grade scale is, it will probably shift down so that we normalize to where we're at in the class. If I happen to give that too hard, okay. That probably makes you nervous. I hope it doesn't too much. I'm really not trying to get you. All right, and then there's a bunch of other questions there. So I think I'll just take questions for a second if you have any. And then I want to set some TA hours or some office hours, and then I'll launch into the technical stuff today. So any questions about the mechanics of the class? I get no read because I have no mouths. I only see eyes and foreheads. So sometimes I can tell a smile, but mostly I just get eyeballs. Okay. We good? Everybody happy? Nod, I guess, if you're like, we're good. Okay, that makes me good. Okay. Let us do, let's get some office hours real quick. So I just figured we could do this in class really quick because I'm going to take this off. I thought we could just take a quick poll of a show of hands and figure out when there's some time. Okay, so you want to just, do you have a thing to pull up your schedule? So or do you know your schedule enough that if I just ask them? Yeah. Okay. So would you guys rather have, so I have a little bit of time on Tuesday, Thursday, or I have time sort of after class-ish, like early afternoons on Monday, Wednesdays. I want to see by show of hands, who would prefer office hours for me, sort of Tuesday, Thursdays? Okay, who would prefer Monday or Wednesdays? Okay, we're like 50-50 on that. And we literally have someone in the back doing 50-50. That's Dan, right? Yeah, you're a DJ assistant, right? Okay, so you don't care. So how is, do you guys have class on Tuesday at 10 a.m.? Does that work? Okay, that works okay. So I will do Tuesday, Thursday at 10 a.m. for my office hours.
She's in your office.
So this is a good question. So I think where I want to do my office hours so that we can be a little more spaced out is in my research offices. So do you know where, so some of you probably know where that is, but the computer simulation, it's on the engineering building on the, what is it, the third floor? Is it the third floor? 312, okay? It's the one with the big glass windows, okay? And I will either be sitting at that table or I will go into the conference room, okay? And there's just a big enough table that we can hold the office hours there. And I think that way, you know, we don't have to sit in my office, and if we can spread out at the table, if there's more than one person, we can be a little more distant stuff. So I'll do that. ChEn, do you know, do you have another time? Do you want to just propose a time and see if or do you want to think about it and send out an email? You want to stress me out? I'm stressing her out.
So you have like Tuesday, Thursday,
I have Tuesday, Thursday at 10 in the morning.
is that like 1 hour session?
Just a 1 hour session.
I can probably do they have classes on Monday, Wednesday, Friday?
I think they have Monday, Wednesday, Friday classes. I don't know, when is, Thermo? It's 10 to 3?
The 10, 11.
10, 11, and 3. Is it, because you're here Monday, Wednesday, Friday, right? So it's probably better for you if it's that day.
Probably do like 1 p.m. to 2 p.m.
1 to 2. Okay.
If that's okay.
So if we have those times, Tuesday, Thursday at 10, and Monday, Wednesday, Friday at 1, is there anybody that cannot come to an office hour? Speak now for a older reason. Okay, just kidding. You can say, you can not hold your peace so that you can say this problem. Okay, so hopefully that'll help.
Where were those on? How was the help?
Same place?
Okay.
No? I mean, you can do where you want, but I assume that's
I mean, I don't have any other place.
yeah, that's her office, right? So, yeah, okay. All right. I think we're good. All right, should we start? Do you want to put the screen up? Should we do some transport? I forgot to get markers to help us avoid. So much to do with that. All right. And you guys read that? That kind of streaky marker. I'll remember next time to put markers in my bag. That's some in the office. Okay, so the first thing I'm going to talk about is, we'll see how far we get into this. We may have to make up a little bit. What is transport phenomena? Okay, that's number one. Number two, number two is the momentum Stitcher law. Okay, and then number three was, oh man, I just had, I forgot it. Oh, yeah, total false. Total false. see if we get to all those today. So the first one is, what is transport? So, I'm going to run next door to you and see if they have an extra marker. See. They're probably over there with rolling and markers. Yeah. Like, stupid telephone here is not going. Okay. So in thermodynamics, right, you learned that systems evolve towards equilibrium, right? You learned about these classical systems that evolve towards equilibrium. And you wrote down, expressions like this, that the entropy 1 over T du plus P over T dV minus the sum of minus 1 n ui over T dn phi. Okay, and this is just the expression for the internal energy rewritten, but for entropy. Okay, and if you remember, you looked at systems like this. Okay, and you probably were at least told that you'll certainly derive in thermo this year the equilibrium criteria. Okay, and it's really pretty simple. It ends up being right that you have two systems and you connect them to each other. Right, you get temperatures go to the same temperature, you get pressures go to the same pressure, and you get chemical potentials that go to the same potential. Right, and so this was thermal equilibrium. This was mechanical equilibrium, and this was chemical equilibrium. Okay, so these quantities, okay, temperature, pressure, and chemical potential, have thermodynamic conjugates, right? They have sort of opposites to them. So we have T, and then we have U, we have P and V, and we have mu, I, and N. Okay, so these here we sometimes call forces, and these guys we sometimes call fluxes. All right, these are all intensive quantities, right? They don't depend on volume. Okay, these are extensive. They do depend on volume. All right, so here, right, with thermal energy, we have energy. With temperature, we have energy. Here, this is mechanical equilibrium. I'm going to sort of fudge it. We're going to talk about motion, okay, and momentum. With this guy, and here we have mass. Okay, so the point of transport phenomena, what we're interested in, is we want to know how, like in thermal, we just say we're at equilibrium. Okay, in transport, we want to say, how do we get to equilibrium? How do we get there? Okay, how in space and time do we evolve towards equilibrium? All right, and we're interested in three systems and three different kinds of phenomena: energy phenomena, okay, momentum, motion phenomena, and mass. Okay, and all of these, all evolve towards equilibrium. They evolve towards the thermal equilibrium, mechanical equilibrium. Okay, so this is important, right, for both, for scientifically and practically, because systems don't actually really reach equilibrium, right? I mean, for practical purposes, they might close enough, but a lot of times, especially in processing a material, okay, or in making a chemical in a plant, you're putting it through a pipe, okay, you put it in a reactor, you do things don't reach equilibrium. You have properties that depend on how they got there, state-dependent properties, okay? And so it matters that you be able to analyze, that transport. Okay, so there are two principles that we're going to need to talk about the fundamental operations. Okay, two principles. first one that we're gonna need are balance equations. Okay, so as you may have noticed, okay, energy and then momentum and mass, these are conserved quantities, right? We can write down conservation laws for them, all right? And so we're gonna need to use that to write down conservation laws and look at how they evolve in space and time, okay? So these, we're gonna get conservation laws for mass, momentum, energy. Okay. And these are going to end up being PDEs. Okay. They're going to be time dependent, multiple spatial variables. Okay. Partial differential equations. Right. And so the mathematical framework that we're going to deal with in transport is solving PDEs. Okay. Usually what it means to solve a PDE is make it into an ODE, okay, and then solve the ODEs. All right. If you can't do that, you basically go to a computer. That's really how you solve PDEs. The other thing that we're going to need, I'll come over here. And number 2 are called constitutive laws. Paper. Okay, so a constitutive law is some kind of relationship between the forces and the fluxes. Okay, so just because I say that there's temperature and energy, that doesn't tell me how gradients of temperature affect energy transport. Okay, if I have a force here, these are like generalized forces, right? They're obviously not in units of force. Okay, you can kind of think about them that way. That's how they're called in non-equilibrium thermodynamics. Okay, and this you can sort of generalize here. You can think about this as a stress, okay, and a strain. Okay, so that would be like a stress and strain here. That maybe helps you see this a little more straightforward. You can actually rewrite this and do this all out with multivariable calculus and show how some of these things arise. But I didn't want to go into the heavy math of that like right off the bat. So if this one plugging in kind of helps me that PV are exactly like momentum and whatever. That comes out because usually do this with these silly 1D examples or 0D examples with pistons and stuff. But it really doesn't have to do with motion. If pressure is causing motion, you can write this down as a stress strain. And what happens in fluid mechanics, right, is that this becomes a strain rate. And that strain rate depends on velocity gradients, as we'll see in a second. Okay. So, but what we need now are some relationships between, these gradients, okay, to say how they go. You already know about these probably. These are things like Newton's law of viscosity. Fick's law and Fourier's law. Okay, so these are relationships that we get out of here. Okay, and I guess I'll talk about that. So I want to just make a quick aside. So if you're like me, you kind of wonder, so where does chemical kinetics sort of fit into this picture? It turns out you can write down force and a flux for chemical kinetics. So the force is an affinity, this little rho, but it's a sum over the chemical potential multiplied by the stoichiometric coefficients. Okay, and then there is a flux, which is the extent of reaction. Okay, and you can think about it this way, but it turns out that it's not a transport phenomenon because gradients of extent of reaction don't drive these affinities. Okay, so chemical kinetics sort of falls in a separate category. It doesn't push things around in space in the same way. It's actually a relaxation phenomenon, and it's also highly nonlinear. So we're going to find that these relationships here are linear relationships. We're going to say that Q, right, is going to be proportional to gradients of temperature. Okay, so these are linear, and chemical kinetics, if you've just had a little experience with it, right, everything's got exponentials in it, right? It's got these Arrhenius laws, okay? So we have a whole separate class then for chemical kinetics, which is also, you know, a kinetic phenomenon away from equilibrium. But it's significantly different enough from transport that it doesn't get lumped in the same way. And the other thing is it's not conserved. So I said gradients don't have that. It's also, there's no conservation law for extended reaction, right? So there's conservation of mass, but you can't say there's some conserved quantity there. So you can't write down the same kind of balance equations. And you can't write down the same kind of constitutive laws. They end up being different, okay? So, okay. So in this class, we're going to have 3 units that we're going to talk about. 3 sort of broad pictures of what we're going to do. So in unit 1, okay, we are going to go through the balance equations and the constituent laws. Okay, for all 3 of these, okay, for mass, momentum, and energy. Okay, we're actually going to start with the constituent laws. So for the first couple of days today, we're going to spend a few minutes on momentum for me, and then we're going to work our way through energy and mass. We're going to talk about these constituent laws, and then we're going to get into the balance equations, and we're going to see the full balance equation. You've probably seen it before. You've probably seen the Navier-Stokes equation. Okay, we're going to start at the momentum equation, get to the Navier-Stokes equation. We're going to look at the full mass balance with different multi-component mixtures. Okay, and we're going to put diffusion coefficients in there and get those out. We're going to do some energy. Okay, and we're going to look at cases where they connect to each other, right? And where we've got terms split well in diffusion equations. So we have convection diffusion, forced convection, heat transfer, that kind of stuff. We're going to just try to understand the structure of these equations, and then we'll solve some simple cases. Okay, so in this case, we'll be mostly getting the balance equation and then solving some like really simplified 1D kind of stuff. Okay, and then in unit 2, okay, we are going to do, what do I call it? I call it solving the transport equations. Okay, so this is going to be math. Okay, a lot of math stuff. So we're going to look at some mathematical techniques and how to address these transport equations. And one of the things that's nice, because they're all balance equations, because all of these kind of linear constituent laws, they look a lot the same. And so the mathematical techniques that solve one often solve all of them. Okay, and so there's these commonalities that we can experience in these different equations to understand. You know, so we might do separation of variables if you've learned that maybe in a class. Okay, to solve PDEs, or you can use a similarity transform. Okay, you can use different kinds of ways to solve these transport equations. And then we'll try and look at, you know, what does this mean? So there's some classic solutions that we'll go through, and we'll try and sort of make sure we get all of those done. Okay, that's unit 2. And then unit 3, okay, are applications. Okay, I'm going to call this selected topics for applications. Okay, because there are just like a bajillion applications of transport. Okay, probably every one of the researchers that you go into, there will be an application of transport in that area. Okay, maybe you're doing, you know, radiative heat transfer, like Dr. Teresa Elder or whatever. Okay, so I'm going to just put that. There's many applications. We will focus on just a couple. Right, we're going to do in here. We're going to do. I think there's a couple of classic problems that they've done traditionally in this class. Okay, like Taylor Harris' version, I think. That's one that comes to mind. Okay, that's kind of a fun problem. And then we have what's called interface transport, which has to do with things like heat transfer coefficients and relationships between dimensionless numbers and some correlations there. And so because this is the first year teaching it, I'm sticking to the things I've taught in this class before. So I make sure we get all that done. But these application selected topics Some of them I like, some of them I don't like. And so in future years, I'm hoping to do some different things with that, just for fun, okay? But all this stuff up here, like from here down to here, regardless of like what order you encounter it in, okay? This is like every county program in the country has to teach this at some point in graduate school, okay? You gotta learn balance equations, you gotta learn the math, to be able to do this. It's sort of the classic thing. That's your training, okay? So that's what we're gonna do. That's why I spent a lot of time in the syllabus talking about it. So I said some of this stuff in the syllabus again. But I'm gonna pause here and just take questions for a second. This is just a super big overview, okay? If it's not all clear, it's okay. This is just meant to sort of give us a structure before I dive into the momentum law, just as the first thing, okay? So any questions? No questions. Okay, I'll put you all to sleep. Also writing and talking. All right. You guys excited? Momentum digital. My nose itches. Can't do this in the thing. I haven't noticed how much I touch my face when I lecture, or when I have this thing on, I keep hitting myself in the head. Okay. So there's two ways we can go about getting a constitutive law. One is by experimental observation. Okay, so you observe a lot of things, you sort of extrapolate from those and make a postulate. Okay, so that would be one, would be experiment, then you make a postulate. Right? When you make a postulate, you say, I've seen this a lot, I'm going to say something mathematically exists. It's, you know, you don't have any proof it's sort of the thing you're hoping is true, okay, based on. Okay, the other thing you can do is you come up with a theory. Okay, there is a theory for this called non-equilibrium thermodynamics. Okay, it was the basis of some of the stuff I was talking about earlier, the entropy equation and forces and fluxes and stuff. Okay, I'm going to do this today. Okay, because it takes, like, this is just be a long math derivation, and it's kind of fun, but you know, let's not let ourselves see too much. Okay, we'll have plenty of time for that later. And if you're interested in this, if you're not yet burdened with homework too much, you can see the book by DeGroot and Mazur by the same title, Equilibrium Thermodynamics. Okay, kind of an older book. It's excellent. There's like chapter 3 or 4 where it talks about this. Okay. All right. So let's think about this thought experiment. Okay, which I'm sure you've seen before. So I'm going to draw a couple of lines. All right, and this is going to be two parallel plates with the bottom plate moving. Okay, this one's going to be at time 0. This one's going to be at some intermediate time, I'll call T1. This is going to be at sometime T2, which is going on a long time. Okay, they're giving me some coordinates here, X and Y. This is just a line for reference. Suppose we can label the fluid somehow. Okay, and at time 0, we just look like this. We're just barely starting to move the plate. Okay, so this was, you know, that started. Okay, at t equals 1, we have some non-developed flow profile. Okay, that we'll learn to solve for in a couple of weeks, and later we'll do this guy. Okay, control freeze on. Right, and so if we say we have some force on this plate, and the plate has an area A, So this would be a force, an area, okay, on the plate. There, we can write down the relationship between the stress and the strain, right? This is all familiar stuff, right? Okay. So I can write down, I can say that stress is the force divided by the area. Okay, I forgot to say how wide the gap was. Let's call that big Y. Okay, and that's going to be proportional to the velocity divided by big Y. Okay, and so that proportionality, that's an observation, okay, that we make here by, looking at this case, looking at what's going on here. Okay, that's our experimental postulate that this is proportional. If that's true, we then say that the force divided by the area is equal to the viscosity divided by Y, where the viscosity here is this constant of proportionality. Okay, so we call this Newton's law of viscosity. Okay, and that's what we're going to think about, stress versus strain. Okay, so you have a fluid, you have something continuously deforming, okay, and those more. There's another way to think about this. So instead of writing this in this way, we can write this with the viscous stress tensor. Okay, and note that Bird has a convention in his book, putting a minus sign here. This is different than all the other textbooks I know that I've used in the past. So just note it. If I screw up, use what's in the first book. Okay. If I forget to write down minus sign. Okay. So we have here let's see, this is the unit normal to the surface. That first one. This is the force component. Okay, so we've got unit normal, so in unit normal Y, force component X, okay, is equal to minus the viscosity times the velocity gradient in the Y direction, velocity gradient in the Y direction, which is linear, okay. Instead of thinking about this as stress and strain rate, we can think about this as momentum transfer, okay. So what we have here is a plate that's moving and has some momentum. All right, and it's transferring that momentum into the fluid, okay, and then that momentum is transferring here and here and here and here, and then over here we have zero momentum. And so at steady state, we have some case where we've got a boundary over here where we have some momentum, a boundary over here we have zero momentum, and we have some linear profile momentum in between. So we can reinterpret this tau yx as a momentum flux. Yx, okay, as a momentum flux. Okay, and recall that flux is something per area per time, right? So if I have momentum is mv, right? Which is, I'm just gonna do a little units thing, kilograms, meters per second, okay? If I go per area per time, so I divide by area times time, I get out meters squared and seconds in the bottom, okay? This little brackets around equals just means it's units that I'm doing. So this gives me kilograms per meters second squared, okay? We can look at the units of that guy, okay? And it is stress, right, which is kilograms. I always think of it as force. It's kilograms meters per second squared. And then per area, right, force per area. So that gives me, I got that from force divided by area. Doing the same thing, right? Kilograms meters second squared. They're the same units. That's not a proof, okay, but it's interesting, right? They're the same units, okay? So we can interpret this as a momentum flux. And so here, this is a momentum flux in the y direction. So the direction of momentum transport. okay? And then the X here, that's the momentum component. Okay, so we're taking the X component of momentum and we're transporting it in the Y direction. Okay, well, that's another way to think about this. So that starts to sort of help us see what's going on here. And if we could think back to what I said earlier, okay, we've made a relationship here between some gradient, okay, which is like our force, okay, and a momentum flux, okay. So we're saying we've got something out here that's pushing momentum around. That's velocity gradients. Okay, so we're out of time. So next time we will pick up hopefully at B, which is we're going to write down. I'll just put this here so we can find it easily in our notes. We're write down a general expression for Newton's law of viscosity. Okay, so we'll do that next time, and we'll launch into some more stuff about energy transport too. Okay, and I'll take a question if there's any. I'll let you go. Which is always a surefire way to get a question. All right. Stay safe. See you Wednesday. Yep, Wednesday. Yep.